Chapter 3, Exercise 26, prove the second halves of parts A and B of Theorem 3K. Now, I've written the second halves down in the screen in front of you. So part A is the image of f under the union of script A is equal to the union of the set of f, the image of f under A for A in script A. And part B is the image of f under the intersection of script A is a subset of the intersection of the set f, the image of f under A such that A is in script A. For non-empty script A with equality if f is single rooted. Okay. Yeah, let's just get on with the proof, shall we? So what I'm going to do is I'm just going to duplicate this, put it down here, and then do the proof this way. So let's do our traditional equality proof. I'm just checking that the pen is not too laggy. Okay. So let's suppose that y is an image of f under the union of script A. Then y is in the range of f restricted to u of script A. Thus, there exists some x. Okay, that is a horrible existential quantifier. xy is an f restricted to the union of A. So xy is an f and x is in the union of script A. Now x being in the union of script A implies that there exists some A in script A such that x is an A. So there exists some A such that x comma y is an f and x is an A. So there exists some A such that x comma y is an f restricted to A. And so there exists some A such that y is in the range of f restricted to A. So there exists some A such that y is an f, the image of f under A. There. So y must be in the union of f of A such that A is in script A. Alright. Cool. So there we have it. And thus f union, the image of the union is a subset of the union of the images, in Enderton's words. There we go. And now the other way around, it's pretty much the same thing. Let's suppose y is in the union of the images. Then there exists some A in A such that y is in the image of f of A. So there exists some A in A such that x comma y is in f and x is in A. So there exists some A in A such that x is in A, which implies that x must be in the union of script A. Thus, x comma y is in f, and x is in the union of script A. So, x comma y is in f restricted to, the union of script A. So y is in the range of f restricted to union of script A. And so y must be in the the image of the union. F image union script A. Thus, the union of the images is a subset of the image of the union. There we go. And then, as usual, all that is left to do is to conclude that the image of the union is equal to the union of the images. Anderton's words, not mine. There. Cool. Alright. Now this is kind of supposing that that script A is not empty. And just as a small aside, let me actually make this blue. If script A is empty, then the union of script A is equal to the empty set. And the image of the empty set is equal to the empty set itself. And the union of the image of f of A such that A is an A is equal to the union of the images such that A is in the empty set, which is equal to the union of the empty set, which is just the empty set. So even if A is equal to the empty set, f of the union of A is equal to the union of f of A such that A is in script A. There you go. Which is unique to the union because the intersection is slightly more subtle. I'm so tired. Okay. Let's get this done so I can go to bed. Alright. Let's suppose y is an f image intersection of script A. Then I'm just going to skip a little bit. Actually, no. Then y is in ran f restricted to the intersection of script A, which implies that there is some x such that x comma y is an f restricted to script A. Now this thing itself implies that x comma y is an f and x is in the intersection of script A. Now x being in the intersection of script A implies that for all A, capital A, in script A, x is an A. So for all A in script A, x comma y is an f and x is an A. So for all A in script A, x comma y isn't f restricted to a. So for all a in script a, y is in the range of f restricted to a. So for all a in script a, y is in the image of f under a. So y must be in the intersection of f image a such that a is in script a. And thus the image of the intersection is contained in the intersection of the images. And this is, of course, assuming script A, what is happening, is non-empty. Okay. One more page. Now I have to show that equality holds if f is single rooted. Assuming f is single rooted, suppose y is in the intersection of all these images. Then for all a in script a, y is in f of script a, right? Then what? For all a in script a, y is in the range of f restricted to a. Thus, for all a in script a, there exists some x such that xy is an f restricted to a, right? Now, since f is single rooted, this x is unique for our choice of y, and thus the same across all a's. And I'm just gonna actually write it out a little bit more clearly, across all a in script a, right? So not only can we say that for all x, for all a and a, there exists some x such that x comma y is an f restricted to a. We can actually say that there exists some x such that for all a in script a, x comma y is an f restricted to a. So there exists some x such that for all a in a, x is in a. So x is in the intersection of a. So x comma y is in f and x is in the intersection of a. Thus x comma y is an f restricted to the intersection of a. Thus y is in the range of f restricted to the intersection of A. And thus, y is an f image intersection of A, and thus what was it? The intersection of the images ends up being a subset of the image of the intersection. Of course, only if f is single rooted. Right, so one tiny thing I wanted to add. You might have caught this, you might have not, but I was missing this intermediate step. So x, y is an f, and x is an A. Right. Okay. So there's that. I don't want to add another page. Let's just put this here. That the image of the intersection is equal to the intersection of the images if f is single rooted. And there we go. I think that is all we had to show. Yep. Cool. Maybe we can also add okay. Yeah, that is all for this exercise. Hope this was helpful, and I will see you in the next video. Bye bye.